That is similar to your avial trees only, similar to rotation, but with it is a self-balancing tree. That in the sense which node you are inserting first, inserting at the last, or recently accessing node will be, we can access it quickly. So it has the property of reaccessing the elements that is recently accessed. So whichever node which you are inserting, that will be made as the a node we are inserting, and that node if you want to access it quickly, what will happen is that particular node, if you make it as a root node only, you can access it quickly, because from whenever a tree is given, it starts with the root node only. So the node which you are inserting at the last, or which even if you want to delete it even, first you have to make you have to make it as a root node, and then you can access whatever you want. That is the performance of for your splay tree. Other things exactly same as your avial trees only. So I think splay splay tree and B tree you don't have implementation. Only till BST and avial tree only you have the implementation. So splay tree is self-balancing and also optimizing, and these are the thing. It is easy to implement than the other trees like red, black, avial, and everything. And less space only it requires, as no balance information is additional information not needed here. So the disadvantage will be the height. Okay, the height of the tree will be always, you can see when I explain, I'll tell you why it is about the height. So normally tree concept itself, if you take, because all tree concept are including binary search tree. So binary search tree will be including the concept of in the normal in your smaller left side smaller elements and right side greater elements. So whenever an element is asked to search or insert or delete, you will not travel through the, maybe unless if your tree is one side, worst case will be maybe n, because if your tree is skewed towards one end, it might happen you will be going through only one end. But also the other thing is, you won't be looking into the, if the, even if the tree is skewed towards left skewed or right skewed, you won't be looking. If it is a left skewed tree, you won't be looking into the right side. If it is a right skewed tree, you won't be looking into the left side. Similarly, if an element is given for insertion or deletion or searching also, you will not go to this end or the other end, only either one of the side only you will be traversing. So that is what always binary search tree. The binary search, you know that if the element is lesser, you will be going to only one side, and other side all you won't look into. So when it is getting reduced, and this is binary, and when recursion applies here, it keeps on reducing again and again, and finally one part only will be done. So that's what it is called as log n. But anyway, the whole derivation you will be learning in your next semester in AD algorithm. Okay, in algorithm paper you will be learning detailed about these explanation of the complexities, all only everything happens in your next sem. So now here I'll tell you about the steps now, then which will make you more clear. Then these are the operations which can be performed: insertion, deletion, searching. These are normal things which we keep on doing it. And splaying means just making it to come at the top. Search, like, except at the end of it, a special step called splaying is done. Splaying means similar to rotation, you will be moving the recently accessed elements to the top. That means playing the tree rearranges the tree so that the element is placed at the root of the tree. That is what I told you. It rearranges by itself. If you attach a node at the last, finally it has to done the rotation, and it has to come that it has the quality of rearranging it and making it to come in the as the top of the root node. So, so the explanations of search and insertion. So from here only I want to explain you more clearly. So splay trees, this step I told you in your avial tree itself. Zig step, zigzag, and zig. For one is zig only, just only one rotation, zig. That is in one side. See here, this side is skewed, means what they are doing is N and P they are rotating. So they are rotating it to like, okay, rotating to this side. Okay, so rotating to this side in the sense n will go as the root node, assuming that n is being inserted. So n will go as the root node and p will come down. Okay, this is what your zig step. Only one rotation is your zig. And zig means, see here in your avial rotation you did double rotations in avial trees. So that is, in another word, in Splay you can tell it as zig step. The zig means same side, either in the left side or in the right side. That is only called as zig. So first what you have to do in this step, the first procedure is you have to rotate this and this PNG. So PNG, when it rotates, it will come like this. Next, you have to rotate N and P. That is the procedure followed in Splay itself, general procedure. So how they are rotating is PNG, then N and P. Okay. So when they rotate PNG, you can see here G should come down. So when G becomes the right side of P, listen very carefully. P is now acting as your root node, so G is now have now coming as the right side of P. So actually, if there is a node in the right side of P, what you should do is you have to make it as the left of the particular node where you are shifting. So that's what I told. If one is K1 and K2, if K2 is added up to first step, K2 will be added to the right of K1. That is the meaning. So this is K1, this is K2. So what I will do is K1, this is K1. Okay. So K1's right will be holding K2's K2. And K2's right will be added up to not K2's right. K1's right will be added up to this K2's left. That is the meaning. So when you, if you have read the code in AVL tree, you would have understood. Last class itself, I told about this. See, when you are rotating, what will happen when you right rotate? If there is a node available in the right side, if see if this node is not there, no problem, just this K2 will be assigned to K1, that's all. But if this node is there, you have to write one more step, like K1's right, that is K1's right will be assigned to K2's left. Okay, K1's right will be assigned to, this is K2, K2's left. So after that you are rotating once again, PNG is rotated. Now N and P, why we are bringing, you can ask me, ma'am, it's already balanced and why we are moving. Splay tree has the concept of moving the recently accessed element should come to the top. So in this diagram we are assuming that N is the recently added element. So when N is the recently added element, main parent, okay, when N is the recently added element, this N should come up. So how to, suddenly N cannot jump and come to the topmost root node. So yeah, we have to follow stepwise. So first PNG is rotated. So P comes first, then N and P will be rotated. So then N comes next as the, now this is made as your root node. You can see. So this is what zig, which is the same step. That may be in the left side or it may be in the right. If it is in the right side, you have to bring like this. You have to rotate this. G has to come top side. So you have to rotate this both. Then you will be rotating this. You will be rotating this both. Then you will be rotating this both. First step, topmost you should rotate. So N will come down, P will go up. Then P and G will rotate. So G will come up and P will come down. It will come in this position. When this diagram is given, this will happen. When this diagram is given, this will happen. So zig means same row or same side. I can tell you same left side or same right side. That is what your zig step. Now coming to zigzag, zigzag will be, you can see here. See here, this is not in the same side. It's consider only G, P and N. Other things, it's an added thing. You leave it out. So G, P and N. Now you see your tree is like this. Your tree is like this. In previous case, your tree was in the same side or either in this side. But now here your tree is like this. So when your tree is like this, what you have to do is you have to follow zig, then only zag. The meaning is double rotation. That is the meaning. So double rotation, how to occur is when a node is like in this form. The node is in this form. First rotate N and G. Okay, N and G. Not N and G. I think here P and N. P and N has to be rotated first. So here that's not. PNN has to be rotated first, so that is right side. So N will, that is what you're actually making for double rotation is when it is like this, when the tree is like this, or when the tree is like this, then this, you have to bring this tree straight like this. And you, or if the tree is like this, you have to bring this node which is here straight like this. Then it will become a zigzag step, but here it is zigzag. So what is, you are going to make it in a straight line. Straight means in the left side, you are going to be in a one particular slanted line. So first rotate N and P. So how to make it slanted, you have to think it over. N and P means it can come, N can come to this side only when you rotate to, when you, only when you rotate like this. Okay, so N will go there and P will come down. N will go up and P will come down. Slowly, step by step only, you have to raise the node to the to make it as a root node. Suddenly it will not jump. So N now first going to this level and P comes down. Now N is in your second level. So after rotation of P and N is now in the second level. Second level means up from the root, I'm telling. Okay, so now you have to rotate N and G. Now when N and G is rotated, N will go at the top and G will come in the G will come down. Okay, so this is what your uh, zigzag step. Okay, so now finally my answer is I have to make N as the root node. I have made also N as the root node. Okay, this is what your zigzag. So when they ask you to splay a node at 1, when they give you a tree like splaying a node at 1 and a tree is given. Now splaying the node at 1 means 1 has to be made as my root node. So you should rotate in such a way that 1 should come at the top. Top as the final answer, my 1 should be the root node. And provided always it should satisfy the BST condition, binary search tree condition. That is very important. Okay, so other things we don't do here. Binary search tree condition is more needed, and 1 should come as the root node. So what you have to do is, as I told you, all are, see here, it is a skewed line. One or maybe the one particular angle, it is skewed. So what you have to do is, when it is skewed, as I told you, first take this step, this alone. Okay, 1 2 3 step alone. So when you take 1 2 and 3 step as this, what you have to do is you have to zigzag step. This is, so you can look here, you can look here. Yeah, when it is skewed, first you will be rotating the topmost, not this one. When it is skewed, 1 minute, 1 minute. Yes. So now what happens is P and N zigzag steps. So what you have to do is first you have to rotate this both. Then only you'll, that is where it will come up. Then only you'll be rotating the other side. So P and G rotated. So P will move up, N will move up. So this is the line which you need to follow is this one. First this one, not this one. Then only it will, the procedure will be right. So when you come here, rotate 2 and 3 first. So when you rotate 2 and 3, 2 and 3. So 2 is rotated like this. That's the meaning. So when you rotate 2 and 3, it should come like this. 2. Then where 3 should come? 2's right side. And 1 will be already here. 1 is already here. And remaining nodes as it is, it will be there. Like next will be, might be 4. Like it will go up till that. Okay, so this is my first step when I rotate 2 and 3. That intermediate step is not drawn here. So 2 and 2 and 3 is my first step. I have rotated. Now 2 has come up and 3 has come down. Now again I have to bring this to, because I'm going to move 1 to the topmost node. So now 1 and 2 has to be rotated. So when 1 and 2 is rotated, this steps come. This step. This intermediate only is only left, that only I have drawn here. Now first I have rotated 2 and 3, so this step will come 2 and 3. Then again 1 and 2 has to be rotated, so 1 will move up. When 1 moves up, it will not 2 will not come in the left side of 1. Why? 2 will not come in the left side of 1. Why? Answer please.
Because BST property would be.
Yeah, yes. 2 is greater than 1. So it should be in the right side only. So don't just, some people, I'm repeatedly telling, because don't make this mistake. Normally, previous students, the regular, what the repeated mistake they do is, instead of rotating, they will just swap in the sense 2 will come down and 1 will go up. That is a wrong. If when you are rotating, if 1 goes up and if you are bringing 2 down, the property is not at all satisfied. You cannot have a larger node on the left side of 1. The larger node of 1 should be on the right side only. So when you rotate, you have to see in the sense that completely you're rotating. 1 will go up. So this step will come after this step, this step. So remaining as such. So now we have taken 1 to the third position now. Now once again, this side you have to take this 2. First this 2 you are taking. Then with this 2. When you take this 2 first, which one we have to rotate? 1 and 4 or 4 and 5? 1 and 4 or 4 and 5?
1 and 4.
Wrong.
Sorry, first 4 and 5 and
Yes.
then accordingly. Yes, ma'am.
Yes. First 4 and 5, because that only will give you correctly. Because if you rotate here, this again becomes a complication. So normally the zigzag step has the procedure of rotating 4 and 5 first, the topmost, then rotate. That means when you rotate this itself, 1 will come to the second position. Okay, so what will happen is, first rotate 4 and 5. So 4 and 5, when you rotate, your 4 will, I'll draw here, your 4 will be like this, and this side it comes, right? So your 5 comes down. Now 1 will be this side, 1. So remaining nodes will be as such, maybe one's right side, right? Remaining nodes will be as such, and remaining above 4, 6 will be there. That will be also as such. Now only you will be rotating 1 and 4. When you rotate 1 and 4, you will be getting like this, 1 and 4. So from this step, when you rotate 1 and 4, that is, I'll draw it neatly. Listen very carefully. Here 1 is there. Here 4 is there. And 5 will come down. No, 4 and 5, no? So 1, 4, and here it will
5
be
will
2.
be the right child of
Right side of
4,
4.
ma'am.
Here it will be 1, 2, 3 only. So when you rotate, here it will come 5. So 1. Okay, so what happens is, now like this, then the remaining nodes as such it will be there. So now you have to rotate 1 and 4. So when you rotate 1 and 4, 1 will come at the top like this. 1 will come at the top, and the right side of 1 will be holding the 4. Because when you rotate, 1 will go at the top, then 4 will come here. The right side of 1, 4 will have. Then based upon when one's right side is having 4, already there is a right node of 2 is there already. So what you have to do, you can make it as, you cannot make it as, again when 4 comes, according to binary search tree condition, 4's left only 2 can be holded in. You'll be comparing the node. That is what actual procedure happens. You'll be comparing the node with, when a new child is being attached at the right of 1, you have to compare 2 and 4. When it is lesser or righter, when it is greater, it will be coming the right side. When it is lesser, it should be added up to the left only. So when you draw it, be careful. Only these problems, play and B tree, you'll be getting some manual problems only. Problems or some general theory questions. If it is in online this mode, physical mode. So you should know how to draw it alone. So one will be, so when the steps come, one becomes, now see from first last step, one has moved till it has jumped 1, 2, 3, 4. It has come till here. Only 6 and 7 now pending. Okay. Now what I will do again, 6 and 7 I will rotate. So 7 will, 6, 7 will come on the right side of 6 and other things remain the same. Finally, I will rotate 1 and 6 at last. So when and 1 and 6 gets rotates, based upon that you have to complete your diagram. 1 will go up, so then 6 will be coming the right side, right of 6, 7 will be there.
Ma'am, but this is wrong, right? The 5
Which
should be
one?
a child of 4 and 3 should be a child of 3. Because
Where,
other than 5 and 3 is smaller than 6, but it's on the right side of 6.
where ma?
In the final answer, yes, where your arrow is,
No, no,
5
no.
and 3 are smaller
Ah,
than 6, but they're on the right side. So this answer is wrong, right?
two's, yeah, two's right side it should come. Correct. So here 1 greater, okay. When you compare 6, this is lesser. This, yes, this should come here. 5 will be coming in the right side of this 4. I will show you. Again 4, 3 will be coming in the right side of 2. Mm. Okay, is that correct? Yeah.
Yes, ma'am.
So this how it should be. I'll change it. Okay. So I think you are clear with this plate tree. So one more example I'll show you. See here. So this is a skew tree, so it will be little bit maybe you have to do it in a proper way. But see here, this will be easy for playing. 10 is there. I'm going to insert 15. So when I insert 15, I normally I'll compare with 10 and 15. So 15 is greater. I will add it to the right side of 10. So when I add it to the right side of 10, I have because it is greater, so added. Now my play tree is recently accessed. What is the recently accessed element? 15. So it should splay after splaying. Splaying means this should come as the root node. So to make it as a root node, where I have to move, which side I will move? I'll be moving to the, I will rotate to the
Left.
left. Okay, so 15 should come at the top and 10 will come at the bottom. 15 top, 10 down. Okay, so now my this is correct. I have made 15 as the root node. Okay, now again I am inserting 12. So each time when you insert, make that as the, see in AVL what you will do is each time when you insert, you will balance it and you will bring, you will balance using balance factor. You will find the balancing things, and if needed, you will be rotating. Here you have to do splaying. Splaying means whatever you insert, make that as the root node. See in this tree, completely this was given initially itself. So, and they have asked us to splay at once. So I am trying to bring it down. But in this tree, only 10 was given and I inserted 15. So next step, I'll be bringing 15 to my root node. Now after that only I will insert next to 12. So when I insert 12, I'll compare with 15 only. Compared to 15, 12 is lesser. Then it should come in the left side. But already 10 is there. So it will compare with 10. When it compares with 10, 10 is 12 is greater, so it should be printed in the right side. So I have printed, but with this I should not stop. If it is a normal BST tree, I can stop. If it is an AVL tree, I will find the balance factor and balance it. If it is a splay tree, what I will do is I will splay it in the sense I will bring the 12 to my root node. So how to bring the 12 to my root node? This is which step, ma? Can you name the step? Zigzag. Okay, zigzag, just like this. Okay, in zigzag step, which node I will first rotate?
10 and 12.
10 and 12. 10 and 12 will be rotated. So what happens? 12 will be, that is 15 I will get first, then I will get the 12, then I will get the 10. So all are becoming in one particular. So 12 will move this side. So when 12 moves, 12 comes here, 10 comes down. So 12 when it moves here, it becomes the same step, same zig line. So now I will again rotate to break the 12 up. I will rotate 12 and 15 now. So once I have rotated left, now I am rotating right. So all trees are interconnected, but the steps which we follow alone will be, there will be difference in each step, but certain conditions will be similar. So now I have rotated to the right side and I will get this answer now. After this step I will get this answer. This step, then I'll get this answer. Okay. Similarly, deletion. So when you want to delete, what you can do? So same thing only, you have to move the deleted node, you have to bring it to the root node and only delete it. Before that you should not delete. So when you bring it to the root node, if it is having one child or two child, follow the condition of your binary search tree. So what will happen is delete 6. So delete 6 has to come in the this side, right, root node. You have to make it as the root node. So here you have to first make 6 as the root node. So move like this before deletion. So 6 and 4 will be in the 6 will come up and 4 will come down. Okay. Now 6 is made as my root node. Now I am ready to delete it. First make it as a root node. That is what Splay tree's condition. Make it as a root node. So 6 I have made as the root node. Now what I will do is, see, when I am deleting 6, it has both left and right child. Okay, so now when 4 and 7 are being deleted, what happens? You know, already in binary search tree condition, what should actually happen when you delete a node with 2 child? Can you remember? You should only tell me. In binary search tree, when you delete a node with 2 child, even in IVL also we follow the same. All conditions are binary search tree condition will be because these all are all the trees are derived from a binary search tree only. AVL or Splay, B, red, black, and everything. So can you tell me which one you are when you want to delete 6? What actually you should do if the node is containing 2 children?
Ma'am, the normal rules, the biggest number of left side or the smallest number of right
Yeah,
side.
right side. Okay, good. So either you have to take the biggest one from the left node or the smallest one in the right node. That is what you should replace actually. Minimum node from the left or maximum node from the left or minimum node from the right. So here in right side, you can see that only one node is there, 7. So leave that option, you leave it out and find the maximum node from the right side. What is the maximum node from the right side? You can, by in-order traversal, you can find the maximum node. Or if any other concept, if you are using also fine, but find the maximum node. So 5 you will be taking as the maximum node. That should be replaced in place of your root node, deletion node. And then you can delete your temp. That is the root node, you can delete it. Okay. So certain things, are concept are same, exactly same as your BST only with very few changes. Okay. So mostly everything will be O of log n because it is a binary search tree, satisfying binary search tree problems. Okay. So next is your B trees. So B tree means it is mainly, this tree will be little bit different than your the representation is different actually. So you are not going to code it or anything. Just listen, understand the concept first, because we'll be getting problems on this. Coding is not, you won't be learning it now. Maybe in the other semesters or maybe in future you'll be learning B tree. I think in DBMS also you will have this. Have you learned DBMS? Database Management System. DBMS, have you learned?
No, ma'am.
There also you'll be having in detail. Okay. So now you understand the concept. Now this concept is only very important because you'll be getting problems for B tree. And for 4th and 5th unit, mainly if it is a theory question, a big question paper, it will be mostly problems only you'll be getting. So understand it, the problems will be very, very easy, and it is easy to get marks also. Because you will have AVL tree problem, B tree problem, and splay trees. Then in fifth unit, you'll be having Prim's, Kruskal's, and BFS, DFS problems all. So if you listen that, it will actually, the problems are very, very easy. So you need not worry about the problem, but listen. So this B tree is actually mainly done for external memory only. Good example for external memory is only B tree. So normally it was designed by Bayer. That's what the name is called as Bayer, no, B tree. So B tree will follow a rule called as, here also BST condition will be followed, but there is another a special rule called as it is order M. An order will be given. Based on that only the tree itself will be followed. M-way tree, it is otherwise called as M-way tree, where each node, that the meaning is where each node can have up to M children, have up to M children. Okay, so M children in the sense, if your order is 5, or if your order is normally they'll give, yeah, 5. Okay, odd numbers only you'll be getting 5, then or 7 or whatever it is, you will be having a that 5 means 5 number of children you can have, and 7 means 7 number of children, not more than that. That is one rule. Another one is it should have a children at least, if I give an order as M, maybe if it is 5, 5 by 2, 5 by 2, that is 2.5. Leave out the decimal part. So take 2, integral part alone. So 2 to 5 children it can have. This you have to keep it in mind, and you have to, each time you have to look into also. So it can have two. Maybe if this is 7, 7 by 2 is 3.5. So 3 to 7 children it can have. That is the meaning. Okay. So your an order they'll give, definitely they'll be giving the order of M if a problem is being asked. So order of M is given means 5 by 2 you have to divide by 2. That is normally a binary search will be having 2 or more children, or 2 children. But definitely 2 children at least. So what will happen is 2 to 5 children it can have. So that's what we are dividing by 2. M by 2 children. It should have at least M by 2 children. And all the leaves should be in the same level. So about this point, I will show you the diagram and tell you, because if I tell, you won't understand. And all leaf nodes should be on the same level, and it can have 2 to M children. Number of keys in the leaf node, this also I'll tell you what it is. This and this I'll tell you. Now see the diagram. A B tree, a normal tree I have, and see here it should be always odd. M should be always odd. So you'll be getting like 3 or 2 or no, 3, 5, 7 likewise only you'll be getting the order. So normally from 5 only they'll start. 3 is a very small tree. Example of a B tree of order 5. See, first binary search tree condition itself is followed. 25 lesser to 25 only you'll be having everywhere. 3, 9, 15 lesser to 3, and see here lesser to 3 here left child. Representation itself will be like this only, and greater to 3 will be in the right side. And for 9 lesser to 9, greater to 9. See, 3 is right and 9's left will be having the same link. And 9's greater right node and 15's left will be having the same. So this is what, and all the nodes are in the same level. And now check, I told you it can have up to 2 to 5 children. So 1, 2, 3, 1, 2, then again 1 to 2, 2 everywhere. And this is having a maximum of 4. Okay. And here it can have any number 2 to 5. Here I told you a line, right? This should have, leaf node should have M minus 1 children only. Number of keys in the each, not leaf node. Okay, I'll tell you that later. You're not confused now. Okay, so this one is, now see here 1, 2, 3, 3, 4. So it is having up till 4. So 2 to 5 children, when it becomes 5, it will become full. So in that case, I'll tell you how to change it. Now look into this alone. This is an example of a B tree only. Now you can look into why this nodes. When I take this is a parent node, this is a child node. Then when this is a child, this becomes a parent. In B tree, what they will tell it as, they can tell it as a children, or even they'll tell it as a key. So the term key, this is called as keys now. So this is a key root node, this is key. So for this node, this will be the keys. So when I consider, see, there are how many sets? 1, 2, 3, 4 sets. Okay, so 4 sets. In non-leaf node there are 4 sets, means your key will be having only 3 set in the sense 1 to 3 keys only will be there. So always this will be m, or non-leaf m minus 1. So 1 2 3 4 sets, this will be only 3. 1 2 3 means this will be only 2. So here there are 1 2 3 sets, 3 sets. So here there is only 2 keys, or two parent, I can tell you. Here 1 2 3 4, 4 sets of children, or 4 sets of children. Yeah, because and each set should have at least 2 to 4 children. Always keep minus 1 children, because 5 means it will become completely full. That is also they won't allow. It will become completely. Normally when you take a queue also, a space will be, instead of making it overflow, it is always better to make it partially filled. At least one space should be vacant. So here when the set, here each set can have 2 children. That is, each set can have 2, or 2 3 4 till 5 it can have. That is what it is given here. Each sets can have 2 to 5 children. Here also consider this as a set. When I compare with 25, this will be one set, this will be one set. When I compare with this will be having how many keys? Always it should be one lesser. So when I take this, it should be 1 2 3 4. So 4 sets are there. 4 sets means here I should have only 3 keys. Similarly here 3 sets are there, only 2 keys. But when I come for here, there is only 1 and 2 sets, that is left and right. Only 2 sets are there. So my root node is only 1. It will be having only 1. That is the meaning. If you understand this, I can proceed to the other things very easily. So now if I want to insert an item, if you can keep on inserting. For example, I'm going to, for the previous diagram only, the diagram is like this. Okay, now the diagram was like this. There is no 12 over here. See here, there is no 12 over here. Now I'm going to insert 12. Where can I insert 12? Can anyone tell me where can I insert 12? 25, I'll compare 12 with 25. It is lesser, I'll come here. It will compare with each key or each child over here, or each sub-child, that is, or 25 child, right? So it will compare with 3, not it is greater. So it will see here. It will see if there is no key over here, directly it can put it over here. But there is another one key, 9. So it will compare with 9. Compared to 9 also, 12 is greater. So next it will see here 15. It will see that 15 compared to 15, 12 is lesser. So it will move here to the either to the left and right of 9 is same link. So what it will do is, you cannot insert anything over here because you have only 4 sets here. So insertion always happens normally in the leaf node only. First it will try the insertion. If it is not possible to do in the leaf node, then only it will jump and go to somewhere else, whether it can alter anything or not. Okay, so normally insertion will happen in the leaf node at the last level only, at the last level. So it will happen it here, but comparison will be starting from the root node. But when it comes to the part, it will check the each and every node, and insertion happens normally in the leaf node. So when it comes to 9, 12 is greater. So it will look into the right side. So when it comes to right side, it knows that there are 10 and 13. So it will compare 10 with 13, and it should be in sorted way. So 10 and 13, 10 it will compare. So it is greater, it should come here. Then it will compare 13 also, it is lesser. So it will be placed in the middle. So I don't want to confuse you with the code now. Code is not needed for you now also. So I will now tell you how the insertion alone. So 12 is compared with here greater, here lesser, here also it is greater, here it is greater. So greater means it should come in the right side. Right side, there are already 10 and 13 only available. So there is space to insert. So it will insert it in the right place in between 10 and 12. Now see here 53. This case will differ. The explanation I have written it here. This case will differ. When you come to 53, now see here 53 should come in the right side of 50 only because 25 greater, 53 is greater than 25. Then 50 is greater than 25. So it will come to the right side of 50. So when it comes to the right side of 50, what happens is so sorry ma. So now here when you insert 53, what happens is it is greater than 25, so it will come to the right side. Then again there is already 37 and 50 available. So 37 and 50 will be compared. So 50 is there. 50 is right side only, it should come. So when you insert to the 50's right side here, somewhere else it will be joining you. Assume that it will join in the after 52 actually by sorted order. So, but what happens is it will have the maximum children. So what we can do, it is a maximum children, always try to have one less than the maximum. So what you can actually do is, this is already containing 4. So what you have to do is, when the particular node becomes full, what you have to do is, it is not allowed actually. So divide the node into 2 halves. So this node I'll tell you. Divide this node. When I insert 53, this becomes full. So divide this node into 2 halves. So when I divide it into 2 halves, what happens is, which is the middle element? 55, 2. So 1, 2, 3, 4, 4 by 2. So it is 2. So when 55 is the middle element. So what I will do is, I will move this 55. I can move. My option is, there is an option in B tree where you can exchange the, add it to the root node, add it to the parent node, otherwise I can tell you. So I will make this, that is just splitting. That's the main concept here. When I make, when I divide this both, now 55 I will move up. Okay, 55 I can move up. And when I add 55, actually, how many sets should come down? When I add 55, one more here, how many sets should come down? If there are
4.
3, yeah, 4 sets should come. But already there are only 3 sets there available. So now when the node, see this you can do only if the node is full. If the node is not full, no worries. You can insert it anywhere. But if the node is full, the diagram before inserting, divide this node into 2 halves. And the middle node, push it up. That is 55 will come here. And my node to be inserted is 53. So I will put it here. 53, I will put it here. In the left side of 55 or in the right side of 50. Now I will change the, now this is being splitted. That is the meaning. This is splitted now. So 67 and 89 will come to the right of 55 and 55's left will hold 52 and 53. So that diagram is here. So this is becoming full. So finally that explanation what I have told is here. And finally this should be the diagram where I have splitted and I have inserted 53 here. 55, that key is now moved up. That is the meaning. So when I can move up, this become 3 keys now. So I can have 4 sets here. One, because left, right, left, right, left, right. So I can have 4 key. 1, 2, 3. My keys also have been increased, or my sets have been increased. And my key is, because my key 1, 2, 3, my parent or node or whatever you can tell the word. So that has been increased. So I will increase my set also. So in insertion, there are only 2 possibilities. One is Directly you can go and insert in the leaf node if the space is available, just like this. Or if the node becomes full, split the node into two halves, take the middle one up, and then increase the set down so that it will be splitted equally. Okay. Now when you see about deletion, delete 12. So 12 is a leaf node here, and if I delete also, it does not affect my any of my result. So I will just delete it, that's all. So I will remove this. So normally 10 and 13. Anyway, it is satisfying the condition like minimum 2 children at least I am having everywhere. So no problem. If I delete 12 also, no problem. I have minimum 2 children. So I will leave it. So that's what the answer is here. Now if I delete 9, see here, I want to delete 9 now. So if I delete 9, there are only 2 keys available, but there are how many sets there? 1, 2, 3, 4 sets are there. So this is not possible in B tree. B tree's main condition is based upon the key over here, I should have sets increased, or based upon the set over here, one should be only decreased. It should be m minus 1 only based upon this set. Now see here, there are 1, 2, 3, 4 sets are there. So if I delete 9, how it is possible to connect this side? Okay, so what is my option for my second case? If it is a leaf node, no worries. But if it is a node with 2 child, then normally that is the condition again we are looking into. It is the node which I am going to delete is having 2 children. So something has to be replaced in place of 9, or else I can, in other way I can tell you there are 4 sets down, so this should have compulsory 3 sets up. So what I should replace? Same concept as your binary search tree. Either take a node, maximum node from the left tree, or a minimum node from the right tree. Same by binary search tree condition. Maximum load in the left tree, if you take, what will happen? Can anyone answer? If you listen, you could tell me correctly. If I take the maximum node from the left side, is it right or wrong? Any one node I have to replace from left or right, I'll have to put it here.
It's
So
better to take from the right side, ma'am.
why we are not taking it from the left side?
Only one will be left, ma'am.
Yes, only one will be left. Okay, so your B tree should have a maximum of 2 to should have a minimum of 2 to maximum children. So max minus 1 you can keep, then only it will not be full. So now what happens is, if you take from here, it is not at all possible. So I will choose it from here. So when I choose it from here, I will replace either from the right side, you have to take the minimum. So I will put the 10 above. That's the explanation is over here. So 10 I will put it up, and I will remove the 9, and 12 and 13, that is also satisfied. So this condition is also okay. Now 10 I have replaced. Now coming to another third case, deletion third case. Insertion, there are only 2 cases. No, you need not worry about insertion. Full and not full, that's all. But deletion, one is leaf node deletion, another one is your node with that is having 2 children, that is a meaning. And another one is delete 16, it is which is not satisfying the minimum basic property. So now I want to delete 16. The leaf node only. Even though it is a leaf node, if there are one more node, I need not worry about deletion of 16. If there are 16, 17, 18, then I need not worry. But if I delete 16, the B tree condition fails, because 15's right node is having only 17. One node is not at all possible. So what should I do actually? So one condition is, either you have to take a node from the left, you can borrow a node from the left or from the right, but here there is no right node, there is no right for this. For 15, see, for 9 I can tell there is a right. Similarly for 3 there is no left, there is 3's left is only 1 here, so it can take only from the right side. For this condition, when I can take either from, for 4 I can, for this set I can take either from this side or from this side. For this set also I can take from here or here, but for this side my only thing is I can take it from here only. So what I should do is, either I have to borrow, if this is having, if my left side of my 15's left side is having more nodes, if it is having more node, I can borrow a node from the left side and put it in the right side. When I put it in the right side, which condition will fail now? If I delete 16,
The
okay,
binary tree normal condition,
binary
man. 13 will be smaller
will,
than 15.
yes, 13 will be smaller than 50. So what should I do now? Based on the previous technique, you can tell me where can I
Right,
swap?
right rotation or something like that.
Not rotation. Here it is just like swapping. You will be moving the okay, rotation in the sense even whatever it is. So you will be moving the which node? 13 you can take and put it in the root node. That is, instead of 15 you can place 13 and 15 you can bring down. Is it possible? Because for insertion we did like if it is having a full node, either one node can be moved spared from your child node to the parent node. So what I can do now, the possibility is I have to borrow from this side, left side. But when I borrow from left side, the condition fails because 13 is lesser. So what I have to do is 13 I have to move up and 15 I will bring down. So that is what done here. 13 is moved up and 15 is brought down. So this explanation what I have told is over here. You can read. Now last case is delete 5. So even if this condition also fails, for example, see here, even I'm not able to spare a node. Here also, assume that here also I'm having two nodes. Here also I'm having two nodes. How will I now take a node from the left side? Because both will fail. Any idea?
Make the parent node to
Yeah, make the parent node to
2.
2. Yes, right. So if you make the parent node 2, then I have to bring that 2 here down, somewhere else down. I can make that as the child and bring it down. So how to do that? So I think, yeah. So when I want to delete 5, where is 5 here? Here. Okay, when I want to delete 5, now here there is an option. See, in this case, there is an option. Assume there is no option. I should remove one node actually here. In this case, there is an option. If there is an option, you can use what you can do. If here there is an option of making it without disturbing this node, what can I do? Just as my previous case.
Yes, ma'am. 10 and 9
I
swap
can,
and
yeah,
then
yeah, yeah.
9 and
10,
5.
9 can swap. 10 can go up, 9 can come down. Come this side, come this side. So 10 will move up, 9 will come in the left side. So the problem is solved. Assume that here also there is only two nodes. If here also there is two nodes and if you're not able to swap, then what is my drawback? So what you have to do is make, as he told, you have to make this particular as two nodes and this set as, if this becomes two keys, then this will become only three sets. So how to make three sets is I have to merge the two keys together. So what I will do is I will bring this 3 down and I will delete the 5. So 3 will be down now. So I'll be having only 9 and 15 as 2 and I will have only 3 sets over here. So now see here, I have taken 3 down, 5 is deleted. Now only 1, 2, 3 sets. So this is one possibility of deletion.